Hello, we're going to talk about quantitative comparison of physiological effects between aortic stenosis and the bileaflet valve replacement. My team members are Pedro, Eduardo, Gladys, and me, Mariana. According to the World Health Organization, cardiovascular diseases are the number one cause of death globally. An estimated 17.9 million deaths were caused by cardiovascular disease in 2016. Cardiovascular problems may be found on the vasculatory or the heart itself, including the valves. Worldwide, the most common valve disease is aortic valve stenosis. Aortic valve stenosis is the narrowing of the aortic valve opening. This restricts blood flow from the left ventricle to the aorta, also affecting the pressure produced in the left atrium. The causes for aortic valve stenosis may be congenital, or from old age, or even as a consequence of rheumatic fever.
One of the first effects that stenosis causes in the cardiovascular system is the increase in resistance to blood flow. As this happens, the left ventricle fails to empty adequately, reducing the net stroke volume and the aortic pulse pressure. This forces the body to activate coping mechanisms to increase blood volume, which in turn raises the venous return, so the left ventricle needs to increment the pressure generated during systole, leading to ventricular hypertrophy and the fall of cardiac output. This will eventually lead to a heart attack. Aortic valve stenosis also affects other organs. When trying to increase the blood volume to compensate the loss of aortic pressure, the renal output will be diminished and more red blood cells will be generated to fight the hypoxia. On severe cases, pressure levels will also rise in the left atrium, inducing serious edema in the lungs. There are several cases in which it is necessary or recommended to do an aortic valve replacement. In order to know when it's better to have a surgery, this table can be used. It is especially necessary for patients reaching stages C2 or D1 to have a valve replacement, because if no change is done, the rate of death is more than 50% in the next 2 years. There are two types of replacement valves, bioprosthetic and mechanical. The first ones are created for porcine aortic valves, and the second ones are completely man-made, so they are usually preferred. From the three main types of mechanical valves that exist, the bileaflet valve is the most common in the market. It is composed of two semilunar discs attached to a rigid valve ring which is sewed to the entrance of the aorta. The opening angles of the leaflets range from 7 degrees to 90 degrees, creating three different size orifices that permit blood flow from the ventricle to the ascending aorta.
One of the main disadvantages of bileaflet valves is the backflow caused by the valve not sealing completely. This backflow causes abnormal flow and hemolysis in the blood cells. This also adds to the list of typical problems in mechanical valves, which include hemolysis, thromboembolic events, and detachment. Even taking all these problems into account, the bileaflet valve is the most common for replacement because it produces the most linear and natural flow possible. Our objective is to review more in depth the physiological effects of different stages of aortic stenosis on the flow type and velocity at the site of the problem, and compare them to how those parameters change after a replacement valve surgery.
For the simulations, we used SolidWorks software and created three different cases, two for the stenotic valve and one for the leaflet valve. In order to have the same conditions for every simulation, we chose a set of parameters and designed the models around them. The first is the radius, which is 24.54 millimeters, and the height, which is 10 millimeters. Once we had the 3D models, we begin our test. For the fluid simulation, we use an inlet volume flow of 5 times 10 to the minus 5 cubic meters over second. This is the only parameter because our main goal is to see how the fluid behaves on an stenotic valve and how it improves if there is a valve replacement. For the first simulation, we have the case of mild stenosis, which has an area reduction of approximately 50%. Here we can appreciate two figures, the one in the right, which is the vorticity plot. In this plot, we can appreciate how the fluid becomes turbulent as it enters the valve, having the highest effect right at the tip of around 180.47 1 over second, and slowly fades as the blood continues its path through the aorta to 53.65 1 over second. On the other hand, the right plot is the velocity of the fluid. As the area reduces, the velocity of the flow begins to increase considerably, having a peak of 0.263 meters over second. What is really interesting of this simulation is that the walls of the aorta At the walls of the aorta, the velocity is very slow in comparison to the center. This effect is being caused by the turbulent flow caused by the stenosis. The second simulation is severe stenosis. At this degree of the disease, the valve has an area reduction of approximately 75%, where the path is very narrow, and in the figure of the right, we have once again the vorticity plot. In comparison to the mild stenosis, the turbulence is gathered more at the center of the valve. This causes an increment of vorticity from 184.47 1/2 in the previous simulation to 373.13 1/2, which is more than double. There is also a similar effect where the fluid slowly loses its turbulent behavior and the vorticity decreases to 159.92 1/2. At the right, we have the velocity plot, which also shows an increment from 0.263 meters over second to 0.8 meters over second at its peak. A similar effect can be seen here where the velocity slowly reduces near the walls of the aorta.
For the third simulation, for the bileaflet valve, an approximation of the Medtronic Advantage model was used, with the same parameters from the previous simulations. For this bileaflet model, a ring of 24.52 millimeters was used as a base, and two leaflets were placed parallel to the artery and 2.13 millimeters apart to simulate the stage of a completely open valve. The leaflet consists of two parts, the hinge and the semi-ellipse. The hinge has a height of 1.79 millimeters and a length of 24.31 millimeters. The first radius of this semi-ellipse was 24.31 millimeters in order to match the hinge, and the other one was 11.85 millimeters in order to be able to touch the rim of the ring on the closed face. Considering that this fully closed valve will have an angle of 64 degrees from its open position. First, we simulate the vorticity when the valve is open. So we got this image where we can see that the maximum vorticity is right next to the valves on the outer openings, but this vorticity only gets up to 81/2. Then we have the flow lines and the velocity on the same simulation. As we can see, we have an almost laminar flow, which is really good. And with the velocity, we have a small difference between the velocity on the outer openings and the velocity on the openings between the leaflets, getting a maximum velocity of 0.144 meters over second. Then we simulate the flow when this valve is closed. As we said, one of the major drawbacks from this valve is the backflow generated because of the valve doesn't perfectly seal.
In this table, we are comparing the most important values obtained from the simulations. Here, we can observe that maintaining a low blood flow velocity is crucial for the patient's health. Even with mild stenosis, velocity is almost 4 times larger than with a bileaflet valve. Velocity itself is affected by the size of the aperture of the valve. If this aperture is small, velocity and pressure increases, meaning that the left ventricle will need to exert more pressure during systole to achieve this velocity. Velocity also affects the type of flow. This type of flow we want to achieve is linear because turbulent will wear endothelium cells over time, affecting the health of the blood vessel.
As it can be seen from the values obtained on the simulations, as the stenosis worsens, the flow is critically affected, becoming more and more turbulent. This is the reason of the murmur that can be heard during auscultation between the first and second cardiac sounds. We can also see that the bileaflet valve improves the effects of the disease on the blood flow, which goes back to a linear behavior. This proves that the valve replacement is an effective treatment. Nevertheless, the replacement involves a complicated surgery with many possible risks, and patients have to take anticoagulant medication for the rest of their lives, so surgery should only be considered if absolutely necessary.